This lesson is on equilibria and stability of ordinary differential equations. And what are these things? What do they mean? Well, most crucially, they're concepts that let us talk about the long-term behavior of a differential equation model of change. Right? So if you have an ODE, it's describing something that changes in time. One of the most pertinent and most important questions that often needs to be asked is, what does this differential equation do in the long run? And the concepts of equilibria and stability are ways of talking about that. In short, equilibria are states where the function or functions don't change anymore, which means that if your dependent variable is x of t, it means the derivative is 0. Or if you have a system of equations for x of t and y of t, that they're both 0. And I'll do an example for you of these later on, but basically you use algebra or a computer to solve those equations and find out for what values of x or x and y you have equilibria. Stability refers to what happens if you move a little bit away from the equilibrium value. And if you move back towards the equilibrium, we call it stable. If you move far away from it, we call it unstable. And sometimes there might be a situation where you orbit around it, and I'll show you pictures of that, and that's called neutrally stable. Now, in a more advanced course, you might learn some more mathematics behind these ideas and maybe make them a little more technical and learn how to calculate them more exactly. But in this course, we're basically going to address these concepts using pictures. So let's start with an example. This is equilibria and stability for a single ordinary differential equation, and this is the logistic growth model. The logistic growth model, if you recall from previous screencasts, is the model for a population that grows in the presence of constraints. So here, let's let x of t be the number of organisms in a population at time t years, and the differential equation is dx dt equals minus 0.2x times 100 minus x. So one question is equilibria, which means are there any values of the population x such that if the population happened to have that value, it would stay exactly at that value. And so we look for when things don't change. And so that means we set a time derivative equal to 0. dx dt equals 0, or another way of writing that is 0.2x times 100 minus x equals 0. And just from eyeballing this, there are two solutions. Either x can be 0 or x can be 100. Okay, and this sort of makes sense, right? In that if there's no one in the population, there will be no one forever because there's no one to reproduce and make any other organisms. Then there's this other equilibrium value, 100, and that corresponds to the carrying capacity of the population, and we'll see that maybe a little bit more in a minute. To assess stability, what we usually do is draw a number line, and this is a number line for the dependent variable x, and we try to put down our equilibria and figure out what happens in between them. So one equilibrium is right here at 0, and then there's an equilibrium out here at 100, and of course we can't have negative values of the population, which is why I'm starting here. Okay, so we basically just want to test different regions and write down in different regions what is dx dt. Well, we know already that at these 2 points, dx dt is 0. That's how we found those points to begin with. They're equilibria. What about way out here? If x is bigger than 100, then this term here will be positive, and this term here will be negative. A negative times a positive is negative. That means dx dt will be negative. So what I'm going to do is put a minus sign out here, but really, more pertinently, I'm going to go on this line and draw a leftward arrow in this region on our number line. And the reason is that if dx dt is less than 0, if it's negative, that means x wants to decrease, right? X decreasing means the population getting smaller. That means moving to the left on this number line. Okay, let's try in between here. You can pick a point in this region, say 50. 100 minus 50 is positive. 0.2 times 50 is positive. So dx dt will end up being positive in this region. And so I'm going to draw a right arrow, because if x happened to have a value in here, then dx dt would be positive, the population would want to increase under the rules of the differential equation, and you'd want to move to the right along this number line. Okay, so this is an incredibly useful and powerful kind of graph to make because it basically shows you the different possible behaviors of this differential equation depending on where you start out. If you start out with a big population, you're going to decrease and move towards 100, and that's because the population is too big and the limited resources can't support all of those organisms. On the other hand, if you start in this region here, then the population will increase in size and approach that carrying capacity of 100. Now we can talk about stability, and to assess stability, what we imagine doing is standing on a particular equilibrium value and kicking ourselves off of it a tiny amount and seeing what happens. So for this equilibrium here, if I kick myself off a little bit to the right, well, I notice that in this region, the arrow's pointing leftwards, so I would move back to this equilibrium. Similarly, if I kick myself off a little bit to the left, if I killed off a couple of organisms when hunting or something, or they got sick and they died, I'd move a little bit to the left, and these arrows here in this region point to the right, so I would move back to 100, towards 100. And so this is called a stable equilibrium, because if you move off of it a little bit, the differential equation rule then sends you back towards that value. On the other hand, if we look at 0, if we kick ourselves off a little bit, we don't move back towards 0. These rightward arrows send us all the way over here, and we go far away from this equilibrium. So this one is called unstable. So logistic growth model has 0 as an unstable equilibrium, and the carrying capacity as a stable equilibrium. Now let's talk about equations, systems where we have two ordinary differential equations. What we just did for a single ODE was to draw horizontal arrows on that number line to figure out what the equation would do. And for two ODEs, what we're going to do is draw arrows in the phase plane, okay? The phase plane, so this thing we just looked at, this is sometimes referred to as the phase line. It's the way you represent a differential equation when you have one dependent variable. Now we're going to have two dependent variables, x and y, and we're going to represent them in a plane, okay? And the way this works is, let's just, pick a value of x and y. If this is the origin, this is the point 1, 1. And we can see what happens at 1, 1, dx dt is equal to, 1 plus 1 is 2. So dx dt is 2, dy dt is going to equal x minus 2y, that's 1 minus 2 times 1, that's negative 1. So think about what this means. This means that if x happened to equal 1 and y happened to equal 1, dx dt would be positive. That means x wants to increase. That means things kind of want to move to the right, like this. And dy dt is negative, right? So that means y wants to decrease, meaning things want to go in this direction. And what we typically do is start at this point, and then draw an arrow in the direction of 2, negative 1. So that's an arrow in the direction of 1, 2 points to the right, and negative 1. That's 1 point down. And in practice, we usually don't draw the entire arrow going from here to here, but we just draw a little arrow that points in the right direction. Okay, we could then do this at another point. Let's just pick the point, negative 1, negative 1. At negative 1, negative 1, which is right here, dx dt is going to equal negative 1 plus negative 1 is negative 2, and dy dt is going to equal negative 1 plus 2, which is 1. So x will want to decrease, y will want to increase. The error would be negative 2 and 1, something like this. So I would draw this arrow here, okay? And this gets exhaustive if you do it a lot by hand, but what you can of course do is use a computer to do it. And if you use a computer to do it, you get a picture of the phase plane that looks something like this, okay? So here I've used the computer to draw in all of these different arrows for you. And what you could imagine doing to, in some sense, solve the differential equation is just pick a point to start at, that's called the initial condition, and then you just kind of follow the arrows step by step. You could draw even more arrows that are contained in this picture. You just kind of follow the arrows step by step, and you kind of trace out some curve in the phase plane, and that curve is called a trajectory. That's just a representation of the solution of the system of differential equations in the phase plane. Now, it's very helpful and important to connect this to actual graphs of the solutions. So remember that when we talk about the solution to a differential equation, we're talking about formulas or graphs of the function x of t and the function y of t. And I've plotted them for you down here, and I want to connect these pictures to this here. This picture shows y and x, the two dependent variables. This is two graphs showing each dependent variable as a function of time. So time is not explicitly in this picture here, but it is in these pictures here. And you can see that these things kind of map, right? So we picked an initial condition. This was around x equals 0, y equals 2. And when these graphs start out, you see that the x graph is at 0 at time equals 0, and the y graph is at 2. You can see the initial thing that happens as we move along this curve is that first the value of y decreases for a while because we move downwards. But then we turn around and we start increasing. And that's what goes here, right? We decrease for a while and then we start increasing. On the other hand, this curve is moving constantly to the right, which means x is always increasing. So we see this x graph always going up. And we could try to map this out even more. We could look at these plots and we could say in this phase plane, where is the solution exactly at time equals 1? So if I look at time equals 1, well, that's right here. So x looks to be around a value of 2, and y looks to be around a value maybe of, I don't know, a half, something like that. We're a little bit past the point where the y's turn around, so maybe we're, something like this on this graph. Okay, and this is very important to be able to connect these kinds of pictures to this kind of picture here. Now, we still haven't talked about equilibria and stability for systems yet, so let's do that now. We're going to take these predator-prey equations. You've possibly seen these in a previous screencast. I've set all the coefficients equal to 1, just to make things easy. You could think of this as representing worms, which are prey, and they're the prey of robins that are predators that eat them. So to look for the equilibria, we have to ask when are dw dt and dr dt both equal to 0. dw dt equals 0 and dr dt equals 0. That means w minus wr equals 0, and negative r plus wr equals 0. And I think it's helpful to factor here. W times 1 minus r equals 0 on top, and on the bottom, r times negative 1 plus w equals 0. So now we can try to solve things. For the first equation, if this is going to equal 0, there's two choices. It's either w equals 0 or r equals 1. Then we can try to plug those choices into the bottom equation. So if w equals 0, this thing in parenthesis is not 0, it's negative 1. So the only way this equation equals 0 is if r equals 0. So the w equals 0 choice leads also to r equals 0. If r equals 1, then down here, in order to get this thing to equal to 0, this factor in parenthesis has to equal 0, which means that w must equal 1. So we find that there are two equilibria, and their wr equals 0, 0, or 1, 1. Now let's go ahead and try to talk about the stability, and to do that we're going to look at these in the phase plane, and that's what you see here. We have w here, we have r here. You see a bunch of the phase arrows that we talked about before. Here's one equilibrium at 0, 0, here's another equilibrium at 1, 1, and I drew in trajectories. And then we can ask about their stability. So first, please focus on this red point here. The right question to ask in the phase plane for stability is, whether every little shift you could make off of this equilibrium point will lead you back to that point. And if that's true, then it's stable. And so sometimes people look at this picture and they're tempted to say, well, things kind of look like they're going straight down here. The arrows are pointing down, and if I move up, then I should go back down so it's stable. But that's not the right way to think of this. You have to let yourself move off this point in every possible direction, right? So say I move up here. Well, you can see that if you move up in this direction, you'll get swept onto one of these trajectories that then moves far away. Okay, so this point is actually unstable. This point, on the other hand, what happens is if you move off this point a little bit, you neither move much closer or much further away from it, you go in a circle around it. And this is called neutrally stable. Okay, if there were a point such that the arrows pointed into it in every direction, something like this, as an example, then this would be an example of a stable equilibrium. All right, so we've come to the end of this screencast. Ask yourself if you can find equilibria of both single and coupled ODEs, if you can assess their stability using pictures, and if you can connect pictures of the solutions of coupled ODEs to pictures that are in the phase plane. Thanks for listening.